Okay, now how do you do the calculations for the second part of the lab? For this one, we will do a similar method. Okay, for that one, I'm going to draw again my little diagram here. Kind of my free body diagram for my force table. Here I have the center of my force table where all the forces are balancing around equilibrium. And we asked you to hang your mass that I was calling the special mass. We're asking you to hang that mass, which for most of you was a steel ball, but for some of you was a cylinder plus an additional 50-gram weight. We were asking for you in this part to hang that weight at an angle, that mass at an angle of 50 degrees. Okay? So in this case, I'm still going to refer to this angle, this force, as F3. Okay? And so the magnitude of F3, the size of that vector, is going to be the mass of that object times gravity. Okay? And then we asked you to hang the two 200-gram masses somewhere to balance this force vector right here. Okay? So what you should have found is probably, well, let's just pretend some mass that was hanging off in kind of this direction over here, we'll call that F2, and some mass hanging off at this direction here, let's call that F1. Okay? And the magnitudes of those will then be their mass times gravity. Okay? So for this one, really the only one that we know both the x and the y components for right now is this force F3, the one that we asked you to hang at 50-degree angle. Okay? And the other ones, similar to how we did the previous problem, these other ones have some unknown angle that we're trying to solve for in our problem to compare those to our measurements. Okay? But you know what? There's a really simple thing that we can do with this problem to make it a little bit easier for us. There's a little trick, okay? So what I'm going to do is take all of these forces and I'm going to rotate the whole thing by 50 degrees. I'm going to subtract 50 degrees from all the angle measurements that you took and rotate my diagram here, okay? So if you do that, you should find, and I'll go ahead and kind of draw what that should look like. So if you do that, you should find we're going to now place F3 along the positive x-axis. It was sitting at 50 degrees. We subtracted 50 degrees from it, from that angle, and so where it's now lying along the positive x-axis. So the magnitude of it is still M3G. Now if you do that, and then you label your drawing accordingly, you should find F2 up here, and then F3 pointing off down here. The magnitude of, oh sorry, we'll call this not F3, we'll call this one F1. F2 has a magnitude of M2G. And what you should have found, if you did that rotation, now you have a new diagram, that this angle right here and this angle right here are both the same angle. Okay? But I'm still going to call them right now theta 1 and theta 2. Okay, what you should have found whenever you did this rotation is that my angle for theta 1 and theta 2 are approximately the same or about the same. So I can say theta 1 is approximately theta 2. So we can set them equal to each other. So maybe we'll just say that they're both equal to just theta. We'll remove the subscripts on there. Okay? So now, whenever we do our sum of the forces, sum of Fx equals 0, or the sum of Fy equals 0, we're going to have a little bit easier time of it because we now only need to solve for one angle theta, not two angles, which would make for a really tough algebra problem two equations, two unknowns, you could do it, but these angles are embedded inside sines and cosines, so it would make it a little bit unwieldy to do it that way. Okay, so let's just go ahead and let's just work with the sum of the forces in the x direction equals 0 equation. You could do it also with the y equation and get the same answer here. So right now, the way, since I've rotated my my diagram so that F3 lies along the positive x-axis, this vector only has a magnitude in the x direction, and that is just going to be F3, the magnitude of F3. Okay, that's it, the full magnitude of F3, no sines or cosines here. So in this case, F1, or sorry, you need to call that 3. F3x here is actually the mass times the gravity. And there is no y component here because it's lying all along the positive x-axis. But over here, for my forces F1 and F2, I still have to find the x and the y coordinates for them. I'm going to erase this here. I'm going to do this right here. Theta 1 is equal to theta 2, and we'll just call that theta. Okay? So here, if I want to find the components of F1, F1x is equal to the magnitude of F1 cosine theta 1. F1y is equal to the magnitude of F1 sine theta 1. Okay, there we go. Oh, and I have to take care of my minus signs. So F1 is pointing in the negative x and in the negative y. So both of these values have a negative sign on them. And then for F2x, I have the magnitude of F2x is equal to the magnitude of F2 times cosine theta 2. And then I have the magnitude of F2y is equal to the magnitude of F2 sine theta 2. Okay? And now I can plug all of these in over here to my equation for the sum of the forces in the x direction equals 0. So I have my F1x component minus F1, magnitude of F1, cosine theta 1, plus, oh, I forgot again, over here on my F2 vector, the x component is in the negative direction, so we also need a negative x there on the F2 of the x component of F2, but we don't need it for the y component because it's in the positive y axis, along the positive y axis. Okay, so I come back over here to my sum of the forces in the x direction. I have the negative magnitude of F1 cosine theta 1 plus negative magnitude of F2 cosine theta 2 plus, sorry, running out of room, plus the full vector magnitude F3 equals 0. Okay? And I know that, remember that here we have theta 1 is equal to theta 2 is equal to theta. So I could rewrite this equation as I'm going to, in this next step, substitute in everywhere I see theta 1 or theta 2. I'm just going to call that theta because they're both the same. And I'm going to move both of these two terms here to the other side of the equal sign. So I have then the magnitude of F3 equals the magnitude of F1 cosine theta plus the magnitude of F2 cosine theta. Okay, so now I'm going to factor out a cosine theta from these two terms. This is some algebra here. So I factor out a cosine theta, and then I'm left with F1 plus F2 inside the parentheses here. So if I take cosine theta and I multiply it through to F1, and I multiply it through to F2, I get the same thing above this line right here. Okay, so all of this is equal to the magnitude of F3. I'm going to divide both sides by this f1 plus f2. Okay, so whenever I do that, I get cosine theta is equal to the magnitude of f3, so it should be 3, over the sum of the magnitude of f1 plus f2. Magnitude. Okay. Maybe I'll remove these parentheses around here because it's getting a little messy. Remember that the magnitudes of these forces, that's the mass times the gravity of those objects that are making the force there. So just like I did for the other problem, I want to take the inverse cosine of this right-hand side of the equation to get theta. And if I do that, I'll find an expression for what theta should be. Okay? And it's going to be different for everybody depending on which masses you used. Okay? So magnitude of that theta. So if I come back over here to my diagram, I should get that both of these angles are about the same. And then if I find this angle and subtract it from 180, that should give us this angle right here. If I find this angle and add it to 180, I should get this angle right here. So those should match up with the angles that you found from your experiment, except rotated over here such that F31 lines up with the positive x-axis. All right, so doing this calculation and plugging in those numbers, getting some value for theta there, and comparing it to your measurements, your observations, will give you points for that part of the lab.